All right, so now I'm going to prove that Gauss-Legendre methods are algebraically stable, and this is going to rely on some of the tools we developed. That's like just before. In particular, this lemma where it says that if you have a Runge-Kutta method with sort of points C1 to CS, which both satisfies this B2S and CS condition, which is written here, then the famous M matrix is 0, and in particular that means that the corresponding Runge-Kutta method then is algebraically stable, because of course if M is 0, then it is trivially positive semi-definite. Okay? So what we're going to show then by using this lemma is that the Gauss-Legendre methods are algebraically stable. Okay, so let me state the sort of consequence of this corollary. It says that the Gauss-Legendre methods are algebraically stable for all for s greater than or equal to 1. Okay, and if you recall, it's like the Gauss-Legendre methods, where the methods these are the collocation Runge-Kutta methods you get when you use the roots of the orthogonal polynomials, okay, of maximal degree. Okay, so let's prove this. So, of course, the proof strategy basically involves showing that the coefficients of the Gauss-Legendre method satisfy these conditions. Okay, and then once you do that, it's like then you can evoke the lemma. Okay, so the S stage Gauss-Legendre, right? RK method, right, is a collocation method. Of order 2s. Okay. And in particular, it's like the underlying RK method, the underlying quadrature rule, which is sort of the one associated with BIs, is of order 2s. Okay. So the underlying quadrature rule is of order 2s, because it's really just Gaussian quadrature. Yes, it is just Gaussian quadrature. Okay, so what that basically means then is that the sum from 1 to s of bi ci to the k minus 1, right? So this is a quadrature approximation of an integral, which is equal to the integral from 0 to 1 of x to the k minus 1 dx. So going from here to here evokes the fact that the Gaussian quadrature rule is exact for all polynomials of up to degree 2s minus 1, right? And that integral, of course, is that definite integral, of course, is nothing more than just 1 over k. And this has to be true for k equals 1 all the way up to 2s. Okay, so this is just using the fact again that the underlying sort of quadrature rule, which is Gaussian quadrature, is sort of exact for polynomials up to degree 2s minus 1. Yep. Okay, and then hence this means that the RK method, right, the Gauss-Legendre method, is B2S. Okay. All right. So that's not so hard. And then, so by definition of a collocation Runge-Kutta method, right, sort of AKL is equal to the integral from 0 to ck of the Lagrange polynomial. All right, so All right, so I'll write this as tau minus, so I'll write this as the product from j equals 1 to s of tau minus Cj over Ck minus, Cl minus Cj d tau, and this is for k and L from 1 to s. Okay, all right, okay, so all right. So I'm trying to show this condition, and I have this observation. So the sum from j equals 1 to s of a ij cj to the k minus 1 is equal to the integral from 0 to ci. All right, and then the sum from j equals 1 to s, right, the product. Okay, so I have to reindex this a bit. It's okay, so I have ij, let's call that L, k, I guess, k equals 1 to s, right, tau minus ck, and then c Cj minus Ck d tau. Okay, all right. Yes. All right. So yes. I'm sorry, there's something missing. All right, we still have the Ck, Cj to the k minus 1 term. Okay, let me try to do this. Okay, so Cj to the k minus 1, and then the whole thing integrated with respect to tau. Okay, so the observation is the following. So if you look at this, right, this is of course what you would get if you were trying to do polynomial interpolation of a certain function. Okay, so this is the Lagrange polynomial, if you recall, and then this is the value of some function at the point Cj. Okay, so maybe let me sort of do this way. So this thing here, well, sorry, let me write this the following way. So this thing here is the sum from j equals 1 to s of Cj to the k minus 1 times a Lagrange polynomial at the jth position, tau, and then the whole thing I'm integrating from 0 to ci, right, respect to tau. So I want to interpret this now as some function. Okay, I want to think of this thing as some function at ci, and it's easy to convince yourself that this is just f of tau is equal, or f of tau should be equal to basically just tau to the k minus 1. All right. So the upshot, if you will, is that this thing inside the square parentheses is just the interpolating polynomial, which interpolates tau to the k minus 1, but k just has to go from 1 to s, right? And this is a actually, yeah, so k has to go from 1 to s, which means that the polynomial here is at most degree s minus 1. This is a Lagrange interpolating polynomial with s distinct points, and so it is exact for all polynomials up to degree s minus 1. So the upshot, if you will, is that after the dust settles, this thing is really nothing more than tau to the k minus 1. Okay? All right, so after everything's said and done, this thing is the integral from 0 to ci of tau to the k minus 1 d tau. Okay, and this is of course nothing more than just ci to the k minus, well, to the kth power divided by k, which is exactly the condition you need. It's like for this CR condition. And then this is true for I and k from 1 to s, right? So this is the CS condition, if you will. And then this thing here is the B2S condition. Sorry, no, this is the B2S condition. Okay, and then the lemma we had sort of showed before then says that if you have a Runge-Kutta method which satisfies B2S and CS, right, then the famous M matrix is identically 0, and as a consequence it is trivially positive semi-definite, and as a consequence that means that the corresponding Runge-Kutta method is algebraically stable. Okay, so this implies that there's still a little bit to be done. We still have to say something about B coefficients, all right? All right. So we still have to show that the B coefficients are non-negative. Okay, so we also want to show that the weights B1 to Bs forgot. It's like, so you have to, I guess I shouldn't have said that, the lemma says that, it's like m equals to 0 implies algebraic stability. You still need this condition of the weights, right? So you need to show that the weights B1 to Bs are non-negative. Okay, so you let k equals to 1 to s, okay, and then you let f of x be the square of the Lagrange polynomials. Okay. So let's just call that LK x squared. Okay. So f is a polynomial of degree 2s minus 1, 2s minus 2, right? So since it's a polynomial degree of 2s minus 2, it is exactly integrated by Gauss quadrature. So Gaussian quadrature. Okay, and then we also know that the Lagrange polynomials has the property that they have the Quantico delta property, right? So LK C L is equal to 0, right, if k is not equal to L. Okay, so BK is equal to the sum from, all right. Okay, so what I'm going to do basically is that, all right, so we're going to use the Kronecker delta function. It's like as the square of this, right? So we're going to use the fact that this is Kronecker delta function. So LK CL, right? The whole thing squared is also a Kronecker delta function, right? So it's 1 if k is equal to L, and 0 if k is not equal to L. All right. So if you want to take bk, right, you can sum this over bl, and then this Kronecker delta function-like term, right? So that's called a delta KL. So that's a particular way of thinking of delta KL, at least when it's applied to just the quadrature points, right? Okay, so this is F CL. Okay. Okay, and this is from L equals 1 to S. Okay, and again, it's like this thing vanishes, F evaluated CL vanishes unless L is equal to K. And so the only thing which you'll see in this sum is BK, right? So here equal to here uses this Kronecker delta property. All right, okay, but this is equal to the integral from 0 to 1 of F of tau d tau, right? Because this is just the Gaussian quadrature approximation of this polynomial integrand, and the polynomial integrand is of degree 2s minus 2, so it's exactly integrated by Gaussian quadrature, so this is exactly equal to this integral. But of course f is the square of something, so this is so this integral is going to be non-negative. Okay, so that's greater than 0. Okay, and so now we are ready to conclude that the Gauss-Legendre method is algebraically stable because this magic M matrix is 0. It's like by a consequence of the lemma we showed before, and furthermore we showed that the underlying quadrature weights B1 to Bs are non-negative through this argument here. Okay, so this means that Gauss-Legendre is algebraically stable. Okay, so I should have said that. So I made a mistake. It's like when I stated it's like that lemma initially, right? So in the lemma, it's like which I stated at the start of this segment, I said that if the Coda method satisfies the BS and B2S and CS condition, then it is algebraically stable. That's not true, right? But it is true that the famous M matrix, it's like associated that is 0, but and as a consequence, it is positive semi-definite. But we need the positive semi-definiteness of the M matrix together with the condition that the quadrature weights are non-negative to conclude that it's algebraically stable. So there was a little bit more work to be done here. Okay, so let's just stop for now.